In this standard, we're going to be looking at acids and bases. So thinking back to chemical nomenclature, we learned about compounds with a hydrogen as a cation, and we called these acids. That sort of, we said that, if it has a cation, it's hydrogen, it's usually named as an acid, especially if it's an aqueous solution. But we really haven't ever answered exactly what is an acid, or the related term to acids. We talk about acids and we talk about bases. What is a base in a chemical sense? And so in the standard, we're going to be talking about acids and bases. We're going to be looking at various models that are used to explain why acids and bases have the chemical properties they do, and how we can determine what their strength is. So several properties that are in common for acids, or common for acids to have, that scientists have noticed, several over the last several hundred years. Number one is that acids tend to have a very sour or tart taste. So we have like a lemon that we have over here, very tart taste that's in this, or a lot of fruit have that. That is due to the acid that's in that substance, in that fruit. Now, second thing is that if you take an acid and you dissolve it in aqueous solution, is that it conducts electricity. That is, it's an electrolyte. And so if you remember that electrolytes happen whenever substances break up into ions in solution, and those ions can flow. So acids conduct electricity. A third thing that tends to be true about acids, that if you react them with some metals, they'll tend to produce bubbles of hydrogen gas. So you put certain types of metals in acids and they'll create lots of little bubbles, and it's hydrogen. Another thing, that if you take an acid and you mix it with a base, the acid will tend to neutralize the base. And so whatever the base would have done, the base gets sort of canceled out or neutralized by that acid. And then the last one is that there are certain materials that we call indicators. So for example, litmus paper, a type of paper that you put into an acid and it changes colors depending on the presence of an acid and depending on the strength of that acid in some way. And so acids change the color of indicators. Now, what about bases? Several properties that are common for bases. Bases are typically bitter to taste. So acids tend to be sour or tart, bases tend to be bitter. Bases tend to be slippery to the touch. Bases, if you dissolve them, also form electrolytes. They also do conduct electricity when in solution, typically. Bases will neutralize acids. So in the same way that acids neutralize bases, bases neutralize acids. And then bases will also change the colors of indicators, like we talked about litmus paper or a chemical like phenolphthalein, but it will change it into a different color than acids do. And so we can use an indicator to tell, is something an acid, is it a base, and then how strong is that acid or base. So 1884, Savante Arrhenius developed the first really good theory of how acids and bases worked. And Arrhenius basically said this. He said acids are substances that contain hydrogen and produce H plus ions, hydrogen ions, when in aqueous solution. Bases, on the other hand, are substances that contain hydroxide, or sometimes called a hydroxyl group, and produce OH, or hydroxide ions, when in aqueous solution. So we take hydrochloric acid, HCl. Is that Arrhenius would have argued that, hey, if you take this and you put it into solution, it's going to break up into an H plus ion and into a Cl minus ion, a hydrogen ion and a chloride ion. And that what makes this an acid is particularly the fact that it has this H plus right here. And so I already have it written down there. So that H plus is what makes hydrochloric acid an acid. Similarly is that sodium hydroxide, NaOH, is a base because whenever it's placed into aqueous solution, it goes into sodium and a hydroxide ion. But the key is it's that hydroxide ion. That all acids, according to Arrhenius, break up in solution to produce hydrogen ions, H plus ions. All bases break up to produce hydroxide ions, OH. And that's what makes it an acid or a base. Now, note that this does fit in with our understanding from nomenclature that acids are compounds with hydrogen as a cation. Because if it has hydrogen as a cation, that means that it's going to have a positive charge as an ion whenever it breaks up, which would make sense because it's H+. So this is Arrhenius' argument, Arrhenius' theory of how acids work. So this also allows Arrhenius to explain one of the key properties of acids and bases, and that's the fact they neutralize one another. So he said this: let's suppose that we have an acid. If we have an acid, then that acid should have a lot of hydrogen ions in solution. So then we mix in a base. Well, what makes it a base? Having a bunch of hydroxide ions, and so we then have some hydroxide ions that are also in there. And so if you take these hydrogen ions and these hydroxide ions and you allow them to react, the positive hydrogen ion will attract to the negative hydroxide ion and will form water. And as we know, water is a neutral substance. So basically what happens is those H pluses react with the OHs, cancel out, form water, and we no longer have H pluses floating around, so it's decreased the acidity of it. We no longer have the hydroxides floating around. It's decreased the basicness of it, or the alkalinity of it, and so as a result, it's neutralized the acid, or neutralize the base. So this model, this Arrhenius model here, works really, really well for explaining reactions involving hydrogen cation ions, which are sometimes called protic acids, and metal hydroxide bases. Some metal, like say sodium with hydroxide, or let's say barium with hydroxide, right there. It works really, really well for those types of acids and bases. Now, not all acids and bases do fall into these two categories, but we can use this Arrhenius method to understand some important aspects of acids and bases. So, moving on here, let's take a look at some details of what happens whenever you end up with these hydrogen ions in solution. So we talked about you have like hydrochloric acid, it breaks up into H plus ions and Cl minus chloride ions. Now, in reality, very rarely, in fact, actually, we can pretty much say no H plus ion is going to remain in aqueous solution for very long. They do not stay in aqueous solution as H plus ions. And so the reason why is we have to think about what a hydrogen atom is. Hydrogen atom has a proton in the center, has the electrons out in the electron in the electron cloud, and it's going to have one electron if it's a neutral hydrogen atom. Now, there may be some neutrons in it, but for most hydrogen atoms, there are not even any neutrons. It's just the one proton and the one electron that's out in the electron cloud, and that's it. But if this is an H plus ion, that means that electron's been removed. So now we are missing this electron. It is gone. All we have left is just this bare proton right here. Nothing but one positive charge with no electrons around it at all. And so because of the fact that it has no electrons around it, it means other substances that have their electrons can get extremely close to that single proton. We would normally say that it has a high positive charge density. That's the more technical way of saying it here. But what it basically means is that any negatives that get near this proton are going to be attracted to it very, very strongly because they can get extremely close to it. Okay? Now, let's say that we have a little H plus ion. It's showing it down here. You can see it's a little tiny, tiny guy right there because it's not a very large thing, because that proton is itty bitty compared with the nucleus. Is very small compared to the rest of the atom here, but it has a positive charge. So this little positive charge that's down here for this H plus ion. Now a water molecule, on the other hand, remember it has a polarity to it, that the oxygen's more electronegative, attracts the hydrogen's electrons to it, and so we end up with a partially negative end on one side and a partially positive end on the other. It's a dipole. Now, that negative end that's over here is going to see this positive right here, and that positive is going to attract that negative. And so what will happen is that the H plus ion will attract and bond to one of the electron pairs that's on the back side of that oxygen. Because remember, oxygen ends up, its valence electrons are in the second energy level. It's going to have a full 2s subshell. It's got that orbital filled up. It's got, of its 2p subshells, one of its 2p subshells that are filled up. And so let's consider that like this pair of electrons are the two electrons that are paired up in one of oxygen's two full orbitals, or this one is. Hydrogen has no electrons in it now because it's an H plus ion. And so what's going to happen is hydrogen is going to take its empty orbital and overlap it with the full orbital for one of these two oxygen pairs of electrons here. And so this is a special type of bond that's called a coordinate bond. It's very, very similar to a covalent bond. In a covalent bond is that the first atom is going to have one electron, the second atom is going to have another electron. They're going to have two unpaired electrons. They overlap orbitals. In a coordinate bond, we have one atom that has no electrons in one of its orbitals, and the empty orbital overlaps with a full orbital. And so what ends up forming here is, instead of having an oxygen and two hydrogens, we have an oxygen with 1, 2, 3 hydrogens in it, and this substance is called hydronium. So hydronium is an ion, H3O+. So it has 3 hydrogens. You can see that, 1 oxygen. It is an ion and not a compound, not a molecule, because we just added a proton. Water's neutral. We added a positive charge, so it's going to be H3O+. And so this hydronium ion has a +1 charge, and it's going to happen anytime you have an H+ ion that goes in here, because as soon as you basically have released one of these H+ ions, it's immediately going to go and stick to that water molecule, and it's going to end up forming hydronium. Okay, so H plus H2O yields H3O+. And that happens, said, pretty much immediately. And so because of the fact that every single one of these H+ ions is going to immediately bond to the water and form a hydronium ion, we really can say that the concentration of H+ is the same as the concentration of hydronium in water whenever we have any H+ ions are placed there, because they sort of they disappear. They go into that almost immediately. This is what happens. In reality, we don't really have any H pluses, so whenever we talk about with Arrhenius' model that if it's releasing H+ ions, that it's an acid, that in reality it's actually producing hydronium rather than H+, because the H+ is combined right off the bat here. But we'll use those terms sort of interchangeably. Sometimes we'll say H+, sometimes we'll say H3O+. The concentrations are the same either way. It doesn't really matter which one that we use there. So let's see. Here's our next thing to talk about here. Let's look at water. Suppose that I just have a big old container full of water. Okay, nothing but pure water. Now, one thing to remember is that chemical bonds can be broken if a molecule absorbs more energy than the activation energy. Now, if we have, let's say, water, it's at a certain temperature, that certain temperature means it has like an average kinetic energy of a certain amount. But remember that if we heat it up, if we put more energy in the system, then we may be able to have enough energy to sort of get over the activation energy to break those bonds. But that if I have water at some temperature, that doesn't mean that all the water molecules all have the same energy. Instead, it's a little distribution that looks a little bit like this, is that we have like energy increasing along this axis, and this is like the number of particles in here. And so there are going to be some particles that are way up here that have this really, really high energy that may just have enough energy to be able to break one of their bonds. And so in pure water, at any given time, about 1 out of every billion water molecules has enough energy to break one of the hydrogen-oxygen bonds and disassociate. And when we say disassociate, what we basically mean is this. We have a water molecule down here, a water molecule down here. We have this end right here. This is our hydrogen right here. It's got a little positive charge, partial positive, partial positive. The end of the oxygen has that partial negative here. When that positive gets near this negative, sometimes what will happen is that positive will jump over. And so what will happen then is that it'll rebond over here. This bond gets broken. And now if you take a look on this side, what do I have? I have hydronium, H3O+, and I have over here hydroxide, OH-, because I just have 1 hydrogen and 1 oxygen right here. But since it's had one of its electrons, it's got that from this hydrogen here. This hydrogen has gone over to the hydronium, and when it did it, it left its electron behind, leaving that negative, and the hydronium is positive. So this 1 out of a billion that we sort of get here is constantly happening inside pure water. Is that we basically say that water molecules break apart form hydronium and hydroxide. And so this process is called the autoionization of water because it's auto, it does it to itself, it self-ionizes itself, is that it turns into hydronium positive ion and hydroxide negative ion. Now, so it's like, well, why do we still have water then? Well, the reason why is that it doesn't stay disassociated for long. Is that the amount of time that any given water molecule ends up broken up like this is on the order of, I think it's like picoseconds, like 10 to the negative 12th seconds is roughly the order of time this takes. This is an incredibly short amount of time. So almost immediately, this sort of back reaction occurs. So instead of just being a reaction that goes from the water, breaks apart into the hydronium and the hydroxide, immediately is that we get the reaction back the other way so that the hydronium and the hydroxide recombine to form water. So it's an equilibrium reaction. Now, this equilibrium reaction very heavily favors the left side when at equilibrium. We end up with very huge amounts of water and very small amounts of hydronium and hydroxide. Doesn't mean there's none of it, but it means there's a very, very small amount. Now, how much water there is, what the concentration is at equilibrium, and how much hydronium and hydroxide at equilibrium there is highly dependent on temperature. Remember from our equilibrium unit, we saw that temperature does affect the equilibrium. It affects KEQ, the equilibrium constant. Now, for this unit, we're going to be looking at reactions at 25 degrees Celsius. Across the board, we're never going to look at anything else other than that. The same basic logic, the same basic operations works at other temperatures. It just changes the numbers a little bit. And so to simplify things, we're going to stick with 25 Celsius, so roughly room temperature in here. Now, water is constantly undergoing this autoionization process. On average, each water molecule that exists in pure water autoionizes about every 10 hours. And so, you could think of it and almost say that, no water molecule is really that old. They're usually just a few hours old since the last time they autoionized and then reconnected back again. But so this process is constantly going on. Water breaks apart into hydronium and hydroxide. Hydronium and hydroxide recombine back together to form water until it reaches some sort of equilibrium. So that's sort of where we have with autoionization. So here's something that we can sort of note here. Now, since this is an equilibrium reaction, we can write it with a double arrow, write it as an equilibrium reaction, and as any equilibrium reaction we have, it has an equilibrium constant, a KEQ. Now, if we remember our mass, our expression here is that we can say KEQ, it's always equal to the concentrations of the products, which in this case is H plus and OH, raised to the powers of the coefficients. In this case, this particular one, we've sort of rewritten this a little bit. So instead of showing the hydronium, we're just going to call it the H plus ion, because remember we said the concentrations are the same. So, oftentimes we'll sort of do this. It may be more useful to write the equation one way or the other, because originally, we had 2H2O. It was a reversible reaction with H3O plus hydroxide. But really what we're doing here is just like we're saying, hey, we know that the hydronium and the hydrogen ions are the same concentration, so let's almost treat one of these water molecules like a spectator ion, get rid of it, and so we end up with just this guy right here. And so this is just a different way of writing out that same autoionization reaction. It's going to make it a little simpler for this next piece. So we're going to write out our KEQ. So we have our H plus, we have our OH minus. They both have coefficients of 1. In fact, everything has a coefficient of 1 now that we've written this. So these are all to the first power, and of course their first power, then they just sort of go away. We don't really care about them for those exponents here. And so this is going to be our KEQ equation. So once we have this, we can look at a couple things. We're going to look at this water concentration that's on the bottom. When we've done concentration problems in the past, we never talked about concentration of water, and there's a good reason for that. Concentration of pure water is huge. It's about 55 molar. We've never run any concentrations anywhere near that in molarity. Now, since that number is so large, and since the fraction of molecules that break up into into hydronium and hydroxide is so incredibly tiny. We're basically saying, hey, this giant number that just varies by some tiny amount, it's basically constant. That concentration of water doesn't really change a whole lot whenever we're basically water's autoionizing. In fact, it's so small we'll basically treat it like it stays the same. And so because of the fact that it's a constant, let's just go ahead and multiply both sides by that concentration of water, just so we get our two constants, our KEQ and our concentration of water all together here. And so in doing that, it looks a little bit like this. We have KEQ times the concentration of H2O equals the two concentrations of hydroxide and hydrogen ions. And so when we multiply those together, we're going to get a new value, which we're going to call KW, the ion product constant for water. Okay, and so the reason why this is important is because at 25 degrees Celsius, the situation we're going to use, the ion product constant for water is 1 times 10 to the negative 14th. If it's 25 degrees Celsius, it's going to be that number. And so really this equation sort of comes down into this piece right here. While this 1 times 10 to the negative 14th is our KW, this piece inside the box is going to be the one we're going to use. That in water is the concentration of hydrogen ions and the concentration of hydroxide ions multiplied together will be 1 times 10 to the negative 14th if you're at 25 degrees Celsius. And so while KW does vary with temperature, it doesn't vary a whole lot if you add additional ions dissolved in a solution. So this statement inside the box, this ion product constant equation here, is true for pure water, but it's also true if we start dissolving other things into it, like acids and bases, if they're at small concentrations, if they're relatively dilute. And so this is going to be really key in trying to understand things. So we can use this expression for aqueous solutions in addition to pure water. And of course, remember that H plus, that hydrogen ion, we can substitute that with a hydronium concentration at any point because the concentration of hydrogen and hydronium have to be the same, because in reality these H pluses don't really exist there. It's really H3O pluses, even though we can sort of treat them the same way. Now, let's suppose that we were to add a new solute to this that's going to produce some H plus ions. So this would be an Arrhenius acid, okay? And so we'd expect then that if we're adding more H pluses, that the concentration of H plus ions must be bigger than the concentration of OH minus ions. Greater concentration of hydrogen ions at smaller concentration of hydroxide ions. And we can sort of see this a little bit if we go back and look at this equation that we have back here. Is that so? Look at this from the Le Chatelier's principle perspective. Is that if we went ahead and added more H plus, is that we've increased the concentration of H plus. So according to Le Chatelier's principle, the reaction will shift to undo that change to lower the concentration of H plus, and so the reaction is going to shift to the left, which would then decrease the concentration of OH minus of hydroxide in response. And so what happens is that if I increase my concentration of hydrogen ions by adding an acid to it, that should result in a decrease in concentration of hydroxide, and so the concentration of hydrogen ions should be larger than the concentration of hydroxide if it's acidic. So we know this. If you look at the concentration of H plus and the concentration of OH minus, it's acidic if the hydrogen concentration is higher than the hydroxide concentration. It's basic if the hydroxide concentration is larger than the hydrogen ion concentration. And it's a neutral solution if the hydrogen concentration and the hydroxide concentration are the same. And so this is going to let us figure out, is a solution acidic or is it basic, in a calculating way. The key is that we can do this because remember that the product of that H plus concentration and OH minus concentration in all of these situations is always going to be this 1 times 10 to the negative 14th as long as we're at 25 degrees Celsius.